Hi everyone. Last time we talked about the first derivative can help us to figure out local maximum and local minimum, right? When the first derivative is positive, we have the function is increasing. And when the first derivative is negative, we have the function is decreasing. Okay, and if on the critical points, around the critical points, if we have the function decrease and then increase, then we have a local minimum. Okay, so at critical points, when we have the function increase and then decrease, then we have a local maximum. Okay, so that is about the first derivative. And then how about the second derivative? What will the second derivative tell us? Big idea. Concavity refers to whether the graph of a function looks like a bow, like that, described as concave up, or an umbrella. Okay, this is umbrella, describe concave down. The second derivative of a function is positive on the interval where the function is concave up, and the second derivative is negative on the interval where the function is concave down. Big skills, you should be able to use the second derivative of a function to find interval of difference concavity, and also use the sign of the second derivative to tell whether a critical point is an extremum. Okay, so let's look at definition. Concavity and inflection points. Okay, so remember the first derivative, we have critical points. Okay, so now let f be differentiable on an open interval I. If f prime is increasing on I, then f is concave up on I. If f prime is decreasing on I, then f is concave down. Okay, so let me draw a picture. Okay, so let's look at, let me draw the picture here. Okay, so I'm gonna draw two pictures. So this guy and this guy. Okay, so look at the first guy. We can see here, what's the slope? Here the slope is negative. Here the slope is 0. And here the slope is positive. Okay, when x increases, what happened? What's the slope? You can see the slope is negative, is 0, and positive. So the slope is actually f prime is increasing. Okay, so if f prime is increasing, then we have concave up. So concave up is like a bow up. Okay, and if f prime is decreasing, so let's look at the second picture. So here m is like positive, here m is 0, and here m is negative. So you can see when x increases, we have the slope positive, 0, and negative. So actually is decreasing. Okay, is decreasing, then we say the function concave down. Okay, so here we say f concave up, and then here we say f concave down. Okay, if f is continuous at C and f changes concavity at C from up to down or from down to up, then f has an inflection point at C. Okay, so do you remember what is critical point? So let me remind you. So critical point is about f prime, the first derivative. Okay, so critical points is set of 3 conditions. First is in the domain. Second, so it's either f prime is 0 or f prime does not exist. Okay, so here, how about inflection points? Well, inflection points, first of all, it has to be in the domain, like the critical points. Second is either f prime prime is 0 or f prime prime does not exist. So very similar to the critical points, right? But instead of first derivative, we have the second derivative. Furthermore, as one more condition, it requires f prime prime to change its sign. Okay? So it requires f prime prime to change signs. So either from positive to negative or from negative to positive. Okay, then we have inflection points. Okay, can I give you a picture of inflection points? So let's say, for example, this guy. You can see this piece is like concave up because it's like a bowl, right? And then this piece is like concave down because it's like umbrella, okay? So that's why here concave up, here concave down, so it changed concavity. So this guy is an inflection point, okay? Let's see. Okay, yes, so that is inflection point. You can actually see it's like it turns around, it changes direction, okay? So if you have a if we have a car moving right here, okay? So here is like turning to the left, but after this point, it turned to the right. So you can see it's like changing the direction. Okay, so it's called inflection point. All right, we have the test for concavity. Suppose that the second derivative exists on interval I. If f prime prime is positive on I, then f is concave up. Oh, why is that? Well, you know that f prime is a function. So it's okay to take the derivative of the first derivative, okay? And then we get the second derivative, okay? If you can remember, if f prime is positive, then we have f is increasing. So similarly, if f prime is increasing, then f prime prime is gonna be positive. Okay, so positive. F prime prime is actually the second derivative. And here, oops, sorry. Okay. All right, and here, okay. And here, f prime is decreasing means the second derivative, which is the derivative of the first derivative, is negative. Okay, so that's why we can relate the concavity and the second derivative. All right. So that's why we have the second derivative positive, then the function concave up. If the second derivative is negative, then we have the function concave down. If C is a point at which the second derivative is 0 and the second derivative changes signs, then F has an inflection at C, okay? But actually, we not only like the second derivative 0, it could be the second derivative does not exist like this, okay? But because the test for concavity, we assume the derivative exists. So if the derivative exists, it must be 0 at the inflection point, okay? But if we allow the derivative does not exist, then that can be also an inflection point. All right, let's continue. Okay, so you look at this picture. This guy, okay, is like umbrella, so concave down, okay? And this guy looks like a bow, so it concaves up. This guy is like a half piece of an umbrella, so still concave down. Here, like a bow, concave up. Here, like a bow, but half piece of a bow, concave up. Here, like an umbrella, this piece of an umbrella, but still concave down. Okay, everybody? So we mark C is a point of I at which the second derivative is 0 and the second derivative change signs at C, then F has an inflection point at C. However, an inflection point may occur at a point where the second derivative does not exist, like point E in the above picture. So, like this picture, you can see this guy concave up and this guy concave E. Let's see. I mean point D, okay? Point D is not, this is not inflection point. Okay? And D, see, it changed from concave up down to concave up. So this is inflection point. Okay, but however, E is not an inflection point, but the point D is. How about point C? Yes, it's also an inflection point. How about point B? Yes, it's also an inflection point. Okay, how about point P? Yes, it's also an inflection point. Okay. And so you can see this picture, this point T, not only it is an inflection point, but it is also a local maximum. So this is a local maximum as well. Okay. All right. Let's continue. Let's look at example 5. Find intervals of concavity and the inflection points of this problem. So actually this problem we saw last time. But last time we were talking about the first derivative and the interval of increasing and decreasing. Okay, but today we're going to talk about, so in this video we're going to talk about the second derivative and concavity. Okay, so first steps, in order to find the second derivative, we need to find the first derivative first. Okay, so that is 12x cubed minus 12x squared minus 12x plus 12, right? Okay, we need second derivative. So 36x squared, 24x, 12. So we figure out 12 is a common factor. We factor that out. We get 3x squared minus 2x minus 1. Can we factor it? Okay. So that is 3x, that's x, negative 2, so minus 1 here and 1 here. Then we get negative 2. Okay, so after we factor it, we can set it equal to 0. So it's very similar to what we have done, but instead of setting the first derivative 0, we need to set the second derivative is 0. Okay, so we get x equals to negative 1/3 and x equals to 1. Okay. Second, we want to find the domain. Well, this is polynomial, so polynomial domain is all real numbers. Okay, well, do you remember last time? Okay, if for critical points, if the points make the first derivative 0 and it's in the domain, then we can say it's critical points. But actually here, we cannot say they are inflection points because we also need to make sure the second derivative change signs. Okay, so let's draw the table here. So we have, okay, let me fix that. Okay, so we have the real number lines separated by their important points and their possible inflection points. Okay, but we need to check. Okay, so it separates the domain into 3 subintervals. Okay, so what do we care? We care about the second derivative and f. The second derivative, you want to answer with like plus or minus, and then the function you want to answer as concave up or concave down. Okay, all right. Let's see. Okay, so at -1/3 and 1, we get the second derivative is 0 because that is how we get those roots, right? We set the the second derivative is 0. Okay, and we can pick a number in this interval and maybe -1, and we plug in the factored form. So 12 is positive. When we plug in -1, -3 plus 1 is negative. -1 is negative. So 2 negative make it positive. Okay, and here we can pick a number 0. Okay, when we plug in 0, 12 is positive, 1 is positive, -1 is negative, so we get negative. Here we can pick a number, which one? 2, right? Then 12 positive, 3 times 2, 6, 6 plus 1, 7, positive, 2 minus 1, 1, positive. So we get positive, right? So, oops, okay. All right, so that's why here we have increasing, and here we have sorry, we're not talking about increasing and decreasing. Okay, so if the second derivative is positive, we have the function concave up. If the second derivative is negative, we have the function concave down. Okay, and here we have concave up. So find the intervals of concavities and the inflection points. You can see here second derivative change signs. So this is inflection point. And here, second derivative change signs, we also have inflection points. Okay, so we can answer a problem like f concave. So f is concave up on the interval minus infinity to -1/3 and 1 to infinity, and f is concave down on the interval -1/3 to 1. Okay, f has inflection points. Okay, at x equals to -1/3 and x equals to 1. So that answers the problem. Okay. All right, next theorem, second derivative test. Okay, suppose that f prime prime, the second derivative, is continuous on an open interval containing c, where the first derivative is 0. Okay, so if second derivative is positive, then f has a local maximum. If second derivative is negative, then f has a local minimum. Let me draw the picture, okay? If the second derivative is positive, it means we have concave up, okay? So like this guy, C, we know it's a critical point. You can see if the second derivative is positive, so then we have f concave up. We actually get a local minimum. So this is local minimum. Okay, I'm gonna fix my handouts later. Okay, if the second derivative is negative, okay, so here, second derivative positive, we have concave up, so this is local min. And when the second derivative is negative, we have concave down, okay, then this guy is what? Local max. So here is local max. Okay, when the second derivative is 0, then the test is inconclusive. So usually to figure out local max, local mean, we use the first derivative test. Okay, so you look at the first derivative. If first derivative is positive and then negative, we know this is local max. If the first derivative is negative and then positive, so we know it's local mean. So we don't need the second derivative test. And because sometimes second derivative test is inconclusive, so I suggest you to use the first derivative test. Okay, so example 6. To use the second derivative to locate the local extrema of this function, on -2 to 2, compare this with example 1. So we already finished this problem in example 1 using the first derivative test. Okay, so let's use the second derivative test and see what happened. Okay, and so f prime. Okay, first step, f prime is 12x to the 3 minus 12x squared minus 12x plus 12. Okay, and we also want to find the critical points. So if you can remember, we actually did this problem in example 1. Okay, so let's do it quickly here. X squared x 1. Okay, we group them together. Okay, 2 by 2 together. So we have 12. And here x squared and x minus 1. Here x minus 1. And they are the same. So we have 12 x minus 1, x squared minus 1. We can factor out x squared minus 1 to be x plus 1 and x minus 1. So that's why you can combine the two copies of x minus 1 together. Okay, so you set it equal to 0. You know that there are two critical points. Okay, so here are the critical points. Alright, then let's find the second derivative. The second derivative, well, you're going to differentiate. Do you differentiate the factor form or you differentiate with this guy? You differentiate with this guy, right? Because and then you just need to use the power rule instead of product rule. Okay, so we say the differentiate this guy. Okay, so we have 36 x squared minus 24x minus 12. Okay, let's plug in f prime prime of 1. Okay, we get 36 minus 24 minus 12. Oops, that is 0. Okay, by the second tier of the test, no conclusion here. Okay, and because the test is inconclusive. Okay, and how about f prime prime of minus 1? We get 36 minus 1 squared is 1. Minus negative become positive. 24 minus 12. So we have 48. That is positive. So that is why here we have positive means concave up. So this guy is a local minimum. So that's why f has a local minimum at x equals to minus 1. All right. Let's check our answer from example 1. Okay. So example 1. You see, we actually have the local minimum at minus 1, and 1 is neither. Okay, so we can get this result from the first derivative test. And here, second derivative test, we can know one of them is local minimum, but the other one, the test is inconclusive. Okay. All right. So let's continue the next two problems in part C.